Hi again. If you recall, the last topic that we covered in Module 3 was the topic of surface tension and capillary phenomena. We started with a hypothesis. Surfaces can exert forces. If you draw a certain cut into an interface between liquid and air, like for example this cut that I have here, the interface can be curved. The interface can have indeed curvatures that are different depending on which angle you look at the interface. But what was the idea was the fact that for this curved interface, the moment we cut it, there is the possibility for action of tensile or tension-like forces parallel to the interface that tend to exert force in a way that want to kill the curvature and make the surface become again smooth. So this idea that the tensile forces there want to minimize the surface area and are forces that are exerted tangential to the interface, this hypothesis was shown to you by different demos. One nice demo was the moment that we put a paper clip on top of a relatively flat interface between water and air, and we noticed that the paper clip weight can be actually sustained by the curved interface below it as a result of these surface forces that are tangential to the curved interface. And when the interface becomes curved, they have a certain vertical component that can sustain that weight. When there is no paper clip and we just have the interface by itself, and on one side, for example, inside this curved interface, we have water, and on the other side, outside, we have air, this vertical balance of these tangential forces that are coming from the interface will give rise to what we described as Young-Laplace equation. The idea is the fact that pressure inside a curved interface will be larger than the pressure outside the curved interface, and the increase would be proportional to a constant we called surface tension. And surface tension for example, something like water is 72 times 10 to the power of -3 Newton over meter. So it's force per unit line or energy per unit area. And it's a constant that you can measure between different phases and different, even sometimes liquids of the same phase, but immiscible liquids like, for example, oil and water or oil and ethanol. You can measure this. And it has to do something with the chemistry of the interface, but we don't want to enter those discussions that much. We just want to take this constant, and when you multiply it to the parameter 2h, which is 2 times the mean curvature, and that parameter 2h is nothing other than the sum of the principal radii of curvature that you will have at the point of interest that you are looking. For example, here this is the point of interest. That would be 1 over R1 plus 1 over R2. What we learned is the simple idea can be relatively easily expanded to certain geometries that are relatively easy to draw. For example, let's take the case of a spherical droplet. So if I draw a spherical droplet like this, and you have the nice thing that R1 is equal to R2 is equal to the radius of this spherical droplet, R everywhere, then your jump of pressure would be simply Pi is P outside, which is P ambient, plus 2 times sigma times 1 over 2 times the sigma divided by R. So you basically have the 1 over R1 plus 1 over R2, which is your 2h being equal to 2 over R, and you multiply it to sigma. So your pressure has increased by a factor of 2 sigma over R. In a bubble, this result will be 4 sigma over R, because you have not only one interface, you have 2 interfaces. You go from air to the very thin layer of soap and water, and then again from that layer you go back to air. Remember, soap bubbles are air, then a thin layer of soap and water, and then inside you have again air. So you're crossing 2 interfaces. This relationship is used twice. That's why you get 4 sigma over R. But for general geometries that are not easy, like flat surfaces or spheres or cylinders, we need to probably find something slightly more useful and robust in terms of mathematical expression for curvature. And we said that we can actually, at least for two cases, we can derive this relatively easily. One case is 1D surfaces when z, or the height of the plane of interest, is only varying with one component, for example, varying with x, and with y there is no variation. So whatever profile you have, it repeats itself with y, and you can just look at the projection of this surface on the xz plane, which will be zs as a function of x. And then easily you can find the mean curvature, and the mean curvature would be nothing other than, so 2 times h would be simply calculated by this expression. It becomes minus z double prime sub s of x divided by bracket open 1 plus z prime sub s as a function of x squared, the whole thing to the power of 3/2. So that was the expression that we had for curvature for 1D surfaces, and you have certain examples in your homeworks and problem sets that indeed they have a surface that is only varying with x, for example, and in the y direction the profile just repeats itself in an identical manner. At the same time, you can have other problems which are not anymore plane, but are having a symmetry in a different way. They may be axisymmetric. So there is an axis that around that axis, if we take a profile and just rotate that profile around that axis, we can generate those surfaces. For example, many examples of liquid threads, liquid filaments, or jets, they are axisymmetric geometries. They are very much like they follow this cylindrical coordinate system and the symmetry that we have with respect to theta. So you can certainly say that for those problems, d over d theta is equal to 0. And because of that axisymmetry, you can again find the expression for curvature in a relatively easy manner. So for those problems, 2 times h, the 2 times mean curvature, would be two terms. One term would be 1 divided by r multiplied to 1 plus r prime to the power of 2, bracket close, the whole thing to the power of half, 1/2, minus the second term, which is r double prime, divided by 1 plus r prime squared, the whole thing inside bracket to the power of 3/2. And whenever I use prime, whether it was for here, for example, that I had z prime, means derivative with respect to the other coordinate, dz over dx. Consequently, z double prime will be the second derivative of z with respect to x. And here, r prime is simply dr dz, and r double prime is d2r dz over dz squared. And the idea here for axisymmetric problems is the fact that we have two sources of curvature. One that goes as 1/r plus a geometrical correction is the curvature that you have when you rotate around this point. So it's the local thickness of this, for example, neck. But at the same time, we know that that's not the only curvature that we have. It's not the cylinder. You can have a cylinder that will be completely flat here, but still you have a curvature this way. But at the same time, if the axis of the cylinder has a certain curvature, and the way we look at the curvature of the axis of this geometry is through this term, how r double prime and other terms are changing. So if you, for example, have some other sources of curvature that comes from the other orthogonal plane, will be captured by this other term. So you need to take both of them into account, and that would give you the overall curvature that you have, and you can plug it inside Young-Laplace equation, and that would give you the amount of increase or decrease in pressure that you would have as you cross an interface between liquid and air with a certain given density sigma. This idea is very crucial. We use it in many problems that we will solve in surface tension section. But the other thing that we mentioned, that when you cut an interface between liquid and air, on the line that you cut, you should not forget the action of surface tension as a line force, is also something that we frequently use in this section. In the next video, we will give you a nice example and a nice review of that idea. to refresh your memory about this concept and remind you how you can use it in different problems.